Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, welcome everyone, as well as the viewers at home. We're happy to have Evyatar Prokachya tell us about the Cheeger constant of supercritical percolation.
Okay, thank you all for coming or attending at home, as I now discover. Thank you for having me here. So, the title is quite long, but the talk is intended for quite a large, wide audience. So I'll try to define everything besides what asymptotic is and the square lattice. So all the rest of the words will be defined.
Actually, you can get to the core faster. You can skip.
Okay. So you can tell me to run. So how about isoperimetry? Everybody knows the basic facts. So I can skip this. Even the nice fact about the first reference about of isoperimetry.
What we meant is about
percolation. I think we could read the previous slide.
You can go back, but what I meant is you don't have to define percolation.
Okay. So isoperimetry is a general class of problems where the idea is to find sets with a given volume and minimal boundary measure. So these questions were originally asked in continuous space by the Greeks, and they actually knew the correct answer. And as this slide shows, so this actually one reference was saved from Roman times, from 220 BC. It's the story of the Princess Dido, that she was a Phoenician princess that had to run away because her brother killed her husband and tried to kill her, and she ran to northern Africa, where she made a pact with the local king that she will get a bull's hide, and she paid him some money, and the promise was that she will get as much land as she can enclose with the bull's hide. So Princess Dido was a smart mathematician. What she did was take the bull's hide, cut it into very, very thin strips, as you can see here, and then took the seashore as one side and created a perfect half circle as the other side, and of course which solves the isoperimetric problem. And there she formed the kingdom of Carthage, Carthago. So this was all all stated in Virgil's poems. So in discrete settings, the isoperimetric problem is given by the Cheeger constant. I'll just give the quick definition. If you have a finite graph G, the Cheeger constant defined as the minimum over all sets of size smaller than 1/2 the size of the graph, the ratio between the edge boundary, which is all the edges such that one side is in the set and the other side is in the complement, and the volume of the set. Okay. I'll give you one example where application for this. If you take a big torus, so n by n by n in d dimensions, choose a point uniformly at random, then run a random walk until time which is proportional to the volume, so choose some u larger than 0, and run it to time t which is larger than u times n to the d. Then together with Shelef, using a paper of Yuval and Morris, you can obtain, using isoperimetric inequalities, that the mixing time, so you run a random walk on this graph, the mixing time of this random walk is the same as the torus up to an iterated log factor. So this probability that it's larger than iterated log goes to 0 as n goes to infinity. Just one application. It's not the topic of the talk. So skip percolation, skip critical percolation, right? Okay, so we fix some p which is larger than the critical value, and you know that there is some giant component inside the box with very high probability, such that all other components are polylogarithmic in size.
This is bond percolation, is it?
Bond percolation, yeah. I skipped this part. You told me to skip. Uh,
Still
so,
need to tell us what.
so denote the giant component by CDN. Okay, so now this is going to be our graph. And denote by phi and the Cheeger constant of the giant component. Now, in several works by Benjamini, Mossel, Mathieu Remy, Berger, Biskup, Hoffman, Kozma, and this note by Pete in 08, it was proved that n times the Cheeger constant is bounded between two constants, some little c and big C, with probability tending rapidly to 1. This led Itai to formulate the following conjecture that the limit actually exists almost surely. Okay, so the correct asymptotics was known, but not that the limit exists. And so with this conjecture in mind, together with Rosenthal in 2011, we showed that the variance of n times phi n is smaller than some constant n to the 2 minus d, which shows that at least in high dimensions, the Cheeger constant is concentrated around its mean, and it's enough to prove convergence of the mean, but this is still open, okay, essentially. So in high dimensions, we don't even know this.
I'm sorry, what's open? I didn't miss what.
So even the weaker conjecture in expectation is still open. And the topic of the talk today is a paper with Biskup, Louidor, and Rosenthal, which will prove the conjecture in 2 dimensions. So it's not, yeah. So fixed d equals 2, and phi n is the Cheeger constant of father. So the limit in 2-dimensional percolation exists almost surely. Now, the way the proof is constructed is first we'll have to describe what is the Wulff construction. Okay, this is a general physics notion that we'll describe. The Wulff construction is constructed by some norm, so we'll need to define what is this norm that the shape is constructed with. There is some discrete geometrical objects that we had to invent, which to approximate between discrete curves and continuous curves. I'll have to talk about this and the proof of the main theorems. Okay, so what is the Wulff construction? Let BP be some norm. Okay, for now it's the P is just for later use. For now it's just a norm on R2. And let phi p be the solution of the isoperimetric question with respect to the norm beta p. Okay, so it's the infimum over all simple curves in R2 with Lebesgue interior 1. Okay, take the infimum of the length with respect to beta p. Now, Wulff in the beginning of the last century was a physicist, conjectured that such a minimizing curve can be constructed, and he actually conjectured the correct shape. So WP is the ball in the dual norm of beta p. Okay, so if beta p is the L1 norm, then WP will be the L infinity ball, etc. And WP hat is just a renormalization of this, such that you'll have Lebesgue area 1. So this conjecture was made 100 years ago, but it was actually proved by Taylor in 74 that this same shape is indeed a minimizing set.
Which Taylor is it?
I'll check. I'll tell you later. It's not the Taylor, the other Taylor.
Conjecture, was it?
Mm-hmm.
It was really stated as a conjecture, was it? When
By Wulff.
realized it was.
Well, you know, he's a physicist. It was stated as a claim. So. But for us, it was stated as a conjecture, since it wasn't proved. And in 75, Taylor proved that the minimizer is unique up to shifts. Okay, so the Wulff construction is the unique answer to the isoperimetric question. Now, denote by DH the Hausdorff metric, the L infinity Hausdorff metric, for instance. Then a very useful quantitative version that we use in our paper by Dubrushin, Kotensky, and Schlossman says that for any simple rectifiable curve gamma enclosing a region of unit Lebesgue area, if the beta p length of the curves are closed, the curves themselves are also closed in the Hausdorff metric. Okay? Now, using this claim, we also strengthen the conjecture of Benjamini, and we prove a shape theorem. So for d equals 2, and here I state it with the exister norm, but we'll in a few minutes we'll construct this norm. So
Quick question. On the previous slide, is this square root essentially type? Is that the right power? Do you know?
So can it be strengthened? I don't know. So defined by U hat, the family of sets which achieve the Cheeger constant. You show that every set which achieves the Cheeger constant under the correct normalization converges to the Wulff shape with a specific norm. Okay, so in the Hausdorff metric. So this is a shape theorem. Okay, so now for several slides, forget about the probability. We're going to talk about Z2 geometry and topology. So for Wulff's construction, what you need is some sort of tension, right? It was constructed for physical questions, like, for instance, the geometry of a water drop, right? So we have the water tension, but our tension has to do with the with the boundary. So essentially, we need to find some norm which gives us information about the boundary. So there'll be a set of definitions now. So the right boundary edge is the following. So you can look at the definition on top or the pictures which are more clear. So you look at the path, so 3 steps of the path. If the path goes up and then down, then this is the right boundary. These are the right boundary edges of this vertex. Okay, so essentially the law is you go from xi plus 1 to xi minus 1 clockwise, okay? And all the edges which are between are the right boundary edges. So in this case, there's only one. In this case, there are no right boundary edges. And the right boundary of a path, which is denoted like this, is a set of right boundary edges. Okay, so is this clear? Is this definition clear? Now, a rightmost path is a path which is simple, but simple not in the original sense, but in the sense of in the oriented sense. So in each edge, you can cross at most once in each orientation. Okay, and it is rightmost if it is simple and doesn't contain any right boundary edges. So I want to look at this picture. So this is the right boundary path. So which goes like this. Okay.
What did you say? A right boundary path?
The rightmost path. Okay.
It doesn't contain any of its own right boundary.
So yeah, these the striped edges are the right boundary, and you can see that the path does not contain any one of them. And I want you to notice also this curly path, which is on the medial graph. Okay, essentially the graph which, so the vertices are the edges, and they're connected if they share a face via a vertex. And what you can see is, which is a claim, but we prove that for every right boundary path, this interface in the medial graph is simple. Okay, as a path in R2. Okay. So let Rxy be the set of rightmost paths from x to y. For every realization omega of the percolation and the rightmost path gamma, let B of gamma be the size, so the number of open rightmost edges of gamma. Okay. And if x and y are connected inside the percolation cluster, let Bxy be the infimum of B gamma over all rightmost open path between x and y. Okay, so this is on the way of defining the norm. There's one more small definition. So for every vector in R2, let the bracket of x denote the vertex in C infinity that is nearest to x, using, so shouldn't be the lexicographic order anymore, but using some kind of rotational invariant order. Okay. Okay, so theorem, the boundary norm. For every p which is supercritical and every x in R2, the limit b bracket 0 bracket nx over n is an almost sure constant. It is bounded from infinity, and for every x which is different than 0, it's bounded away from 0. The limit also exists in L1, and the convergence is uniform on the unit circle, okay, which is essential for our...
You go back to the previous, so you had B defined.
So bxy, so given two vertices, look at all the rightmost paths between them and the rightmost boundary. Then bxy is the infimum over all the rightmost boundaries of such paths. And beta px is defined as the limit of b0 nx over n. Okay? So the claim is that it is homogeneous. It obeys the triangle inequality. In particular, it is a norm. Okay? So for every p, beta p is the norm that we're going to construct the Wulff construction according to. So this theorem is quite technical, but I want to talk about two conceptual points. So the uniformity essentially comes from this very nice paper of Kesten from '93. It's called The Speed of Convergence in First Passage Percolation, where he invents this nice idea of since so the trajectories are not bounded because you have edges where you cannot cross, so a priori you don't know how far you'll get to. But he has this nice idea of giving some very large weights on closed edges, and then having a new weight which sums up all of these weights, and then this is bounded. It proves the speed of convergence on this thing, and then he shows that it's the same. So this didn't transfer immediately, but this is the main idea. And the second idea is subadditivity. So for first passage percolation, subadditivity is trivial, but here it's just semi-trivial. So the idea is that if you have two rightmost paths, you can concatenate them in the following way. So travel with the first one until the first time you hit the second one, and then continue with the second one from the last time it hits this point to its end. Okay? So it's not very hard to see that this concatenation is the rightmost path, and the difference within the right boundary is at most 2. So a constant difference does not affect the subadditivity, because you can take the norm plus 2 and show that this is subadditive. So these are the main ideas. Now we call a rightmost circuit if it's a rightmost path which is closed. And as we said earlier, it is always possible to find a closed curve which is close to the rightmost path. And we have Jordan's theorem essentially. So you have the interior of this. So the interior of this envelope is well defined. So define the volume of a rightmost path to be the intersection of the interior of the interface, the continuous interface, with C2n. Is this clear?
No, the volume is...
This is definition. So it's essentially all the vertices inside CDN which are enclosed inside...
Or the set?
The set.
So the volume is a set?
No, it should be the size of it, sorry. Okay, now... Now what we need to do is given a set in CDN to approximate its boundary via the norm. Okay.
Section C2, and this is the open. Sorry, C2n was.
It's the giant component.
Oh, okay. So what? But before you use the notation C infinity.
No, at CDN now D is 2, so I put C2n.
You also had C infinity.
Okay,
Yeah.
so,
Okay.
sorry. So I want to talk about how you approximate a set inside CDN to a continuous set such that the length, the beta p length of the curve is close to this. So the first thing you do is a polygonal approximation. Okay, you choose some fixed fixed r, and then jump from vertices which are of distance at least r. So r is an integer. Now, in this process, this polygon that you get doesn't have to be simple, okay? But a simple change just by taking vertices which are very close and creating a polygon with 2 more vertices will produce in a finite time. So each time you do this procedure, the number of components reduces by 1. So this will end at some point. And from the convergence theorem, you know that once these edges are long enough, the b, so the right boundary distance between them will be very similar to the norm. Okay? Is this clear? Good. So this is the theorem which which states what I just said. But we will get to it in a second. Okay, so let's give us. That was quick. Want to look at it? So for every epsilon, there exists a constant such that for every r bigger than 0, with probability which goes stretch exponentially to 1, the following holds if gamma is any rightmost open circuit inside the box of side which is at least r to the 1/5, which is very essential for sets which achieve the Cheeger constant, and the size of the path is smaller or equal than the volume to the power of 2/3, then there exists a simple closed curve lambda such that it is very close to the original one in the Hausdorff metric. Okay, the one is just the.
Now volume gamma is back to being a set.
Yeah. So volume gamma is the set. Sorry. Okay. So volume gamma is what was defined earlier. It's a set that is the intersection of the interior of the interface and C2n. Okay. The one here is just the distance between the discrete and the continuous path. And the beta p length of lambda is smaller, up to some small approximation, than the right boundary distance of right boundary, the number of open right boundary edges of gamma. Okay, so I see that you're a little bit confused. Maybe it's because I confused you. Any questions?
It's the first time It's the first time in 25 years that I've seen volume being. How big is it?
Yes.
What?
So let you know that I didn't like simple for paths which are not simple, but but I will not say more than that. So. Okay, so let's give a sketch of the main theorem. So we want to prove that the limit exists. We do it via lower bound and an upper bound. In the lower bound, we want to start with the set achieving the Cheeger constant, and you can assume that it's larger than some constant n squared. Okay. So by definition, phi of n is the ratio between the. Fellow did it. So by definition, phi n is the ratio between the boundary and the size of an. Now this is a restatement of the previous theorem. So you find a closed curve lambda such that it is close to the original envelope in the Hausdorff metric, and the beta p length is smaller than beta of gamma. Then so since the polygons were chosen to be to include the vertices in the envelope of an, then you know that the best length is better than the original envelope part between the two vertices. So this gives you this inequality. These are volume bounds that you get from the previous theorem. And since you know by density arguments that the size of an is smaller than some, so theta p is the probability of a vertex to be in the infinite component. So the size of an is smaller than theta p plus epsilon n squared over 2 with high probability. This gives you the lower bound on the Cheeger. So phi p is the Wulff number. So I forgot to say. Okay, so this inequality says that since this is a path with the correct volume normalized, it is bigger than the Wulff number. So this is the easier part, the easier side. In the upper bound, we want to start from the Wulff shape, but a priori nobody tells us that the Wulff shape is contained inside a box, right? It's just a solution of some isoperimetric question. So we need to show, so first of all, we need to blow it up to the correct size. We need to show that it's contained in the box. So let's do this. So the red thing is supposed to be the Wulff shape. This is not how it really looks like, but this is for this proof. So let alpha be the maximal number in the x-axis, which is still included inside WP.
Don't you know that it's convex?
Yes. So we're going to use it. It's convex, but I want to show. Yes, but how can you? This is exactly the idea. How can you picture a convex set that lives, so which contains these vertices and leaves this?
I mean, what do you mean? It's in a box. What?
We'll state
every
it.
convex set in some box.
Yeah, but you want to control to bound it explicitly because you want it. You want to approximate it to a set which can achieve the Cheeger constant. So it has to have the correct size inside the correct boxes. So essentially, you need to give a very good bound on the L infinity box which contains it. Okay. So indeed, by symmetry and convexity, you know that if this point exists and also this point and this point and this point, so the L1 ball of radius alpha is contained inside WP. Now, this is why the picture looks ugly because of the assumption by contradiction. So assume that there is some point x, which is to the right of alpha. Okay, so it leaves the L infinity ball. Then by symmetry, you know that also the reflection of x is in the box. So you know that x plus the reflection, which is bar x, so has length which is smaller than 2 times beta p of n. Okay, so this means that x bar over 2 is inside WP, but this is a contradiction. Okay, so so we get these trivial measure bounds, and by normalizing correctly, you know that the normalized Wulff shape contains the L1 ball of radius 1/2 as it contained an infinity ball with radius 1 over square root 2. Okay? So this is not hard, but this is essential for the delineation. Okay, so what you want to do is start with the Wulff shape, and you know by definition that phi p is the length of the boundary of the Wulff shape. Now again, what we do is approximate it by some polygon. Okay? And a polygon which is close enough to the original shape. This you can always do. And now from each of the vertices of the polygon, what we show that you can find paths which are almost optimal. So optimal up to some small epsilon correction, which are as close as we want to the path. So if you take this path, you don't get too far away from the polygon and thus from the original Wulff shape in the Hausdorff metric. Good. Okay, so again, you do the don't tell anybody in this building that I never configured something of Microsoft in my computer. So this is how you find a path inside C.
This will be a little difficult now you've broadcasted.
So this is how we find. So these paths are inside CDN. Okay, they are close to the original set, and their rightmost boundary is smaller. So this is choosing the polygonal and blowing it up to the correct size. This is taking this path and creating this simple circuit with smaller right boundary. And now take all the vertices in the interior of this envelope. Okay, the size is similar to theta p over 2 times n squared. So we get also the upper bound. So is this clear? So each move was a lie. So we have to show that everything happens with high probability. We use the uniform convergence. Right, so where is the uniformity important? In the lower bound, we started from some set, and we did this polygonization. So you need uniformity over all directions, every starting point. In this proof, the uniformity is not as important, but so are there any questions so far before we move to the open questions? So this is essentially a proof for the limit for the Benjamini conjecture in 2 dimensions. So the limit exists, but this is also already very close to the shape theorem, which I will not discuss today. Are there any questions on this proof before we go to the open questions? Okay, so some open questions. So when p equals 1, so what is what is our boundary norm? Essentially, all the edges are open, right? So it's just the L1 norm, right? So the Wulff shape is the L infinity ball, which is what we know, right? If you just take the torus, then such that if the Cheeger constants are squares. Now a square is not smooth because it has corners, but what you can conjecture is once you take some p which is between 1 and pc, it already becomes smooth. This I find very interesting, and at the moment we don't have any idea of how to prove this. Now another interesting conjecture is the limiting shape as p goes to 1/2.
So what do you know about the limiting shape?
So essentially nothing, right? Because it's given. So it's a deterministic. We know that it's some deterministic shape, but it's given by some norm. Now, once you know the norm, you know what the shape looks like. But so when you're very close to 1, it's easy to show that the norm is close to L1, and then the shape is close to the square. It's also not very hard to show that.
What do you mean very close to 1?
So all we know to do now is union bound. So take 1 minus epsilon. When epsilon is very small, then essentially you cannot find a path with. Yes, fixed, but just to win the number of trajectories. This is what I mean. Okay, but essentially we don't even know to prove, for instance, this thing, which is very natural, that when p goes to 1/2, that the limiting shape converges to the Euclidean ball. But this relates to another open question about just the graph distance in percolation, which is also not known. So that the graph distance converges to the Euclidean distance when p goes to 1/2. Another natural question is higher dimensions. So there were some works on Wulff construction in the Ising model that generalized it to higher dimensions by Cerf, Baudieu, Joff, and Velenik. Hmm?
The pronunciation, never mind.
So these generalizations are quite technical, and it's not certain that we can actually use some of this because there is a big difference between droplets and subtle geometric questions like isoperimetric sets. But we're thinking about it. So for instance, it's not trivial even to define the norm, right? So in 2 dimensions, we define the norm via this rightmost path, which is essentially the way we found out you can characterize the envelopes of sets in Z2. But in higher dimensions, you don't have Jordan's theorem, right? You have all these weird sets like the Klein bottle, Alexander's horn sphere. So it's not certain how, given a path, you know what is the orientation of the edges that you're supposed to take. So one way, for instance, to generalize it is to do this twice infimum. So first take 2 points, x, y. For every set which contains x and y on the inner boundary, look at all the paths on the boundary of the set. Now the set's boundary gives you the correct orientation of the path's boundary, and now take infimum over all the sets over all the paths. But then, so we're thinking about it. It's not easy to show subadditivity, that it converges. Certainly, uniform convergence will not be easy. But hope that it will succeed. Okay? Questions?
Yeah, so I still didn't quite understand what you know and what you don't know about the shape. So, for instance, it's usually fairly standard to argue things about the curvature of the Wulff shape. But if you knew how to do that, then probably you wouldn't have placed that open problem at the end.
Sure.
So what do you know?
So again, we get the norm by the subadditive ergodic theory. Basically, it's not very constructive, right? So we know that there is some limiting shape. We have a characterization of it, but...
So this is supposed to think about this as the surface tension?
Yeah, exactly. The norm is the surface tension. This is a restatement of...
So you don't understand the second derivative of it? That's a problem.
Yes. Yes.
You can carry out the calculation. Okay, usually,
so
like something imperative is to know that the second derivative is strictly positive at 0 or something like that.
So
it's hard
again, probabilistically, the norm is not very hard to understand, right? Given a path, you have the boundary, so it's not hard to do the calculations and use the norm even though you don't know what it is. So all we need is this bound to say that if points are far away, then the best path is close to the norm. It's not immediate, and we need all this technology of Kesten, but this is possible without knowing, right? Like you have all these supercritical claims when you don't know what the critical number is. So many things are possible to do without knowing what it actually is. So we know that there exists something, it's deterministic, but we don't have a Sure. Yes, you know that. Yeah, but so it is the dual ball of some norm. So it's nice, but which norm? That's the question, right? And you pass from a square to a circle. By what way? What are the fluctuations? These things are interesting and very open.
Thank you, Peter.
Okay.